Hello students, in today's lecture we are going to solve NCERT exercise problems from 12.1 to 12.2 and 12.4 to 12.10 on kinetic theory of gases. This is disclaimer. Learning objective. By the end of this lecture, you will be able to solve questions on kinetic theory of gases by applying concepts of ideal gas law, kinetic theory of gases, mean free path, RMS speed, collision frequency, and gas laws at STP using proper reasoning and calculations. So in today's class, we will cover NCERT exercise problems on kinetic theory of gases. There are total 10 questions in this exercise. We are going to cover 9 questions from 12.1 to 12.2 and 12.4 to 12.10. Alright. Estimate the fraction of molecular volume of the actual volume occupied by oxygen gas at STP. Take the diameter of an oxygen molecule to be 3 angstrom. So here you have to find out the fraction of molecular volume to actual volume occupied by oxygen gas. Let's see the solution. So let's begin by listing the given information. We know that we are working under STP temperature and pressure conditions. STP, standard temperature pressure. Alright. So diameter of O2 molecule is equal to 3 angstrom, which is equal to 3 into 10 raised to the power minus 8 centimeter. Actual volume occupied by 1 mole of oxygen gas at STP is equal to 22.4 liter, which is equal to 400 centimeter cube. Avogadro's number, Na equal to 6.023 into 10 raised to the power 23 molecules per mole. Alright, and radius R equal to d by 2. So we know the value of d, 3 angstrom. So divide by 2, it will be 1.5 angstrom. 1.5 angstrom means 1.5 into 10 raised to the power minus 8 centimeter. Alright. Now we will calculating the molecular volume of oxygen gas. Here we are focusing on the molecular volume, which is the space occupied by the molecules themselves. The formula for molecular volume is given by V equal to 4 by 3 pi r cube n. Here R is the radius of molecule and n is Avogadro's number. Alright, and n is Avogadro's number, which is equal to 6.023 into 10 raised to the power 23 molecules per mole. So now we substitute the values into our formula. V equal to 4 by 3 into 3.14 into 1.5 into 10 raised to the power minus 8 whole cube into n, that is 6.0 into 3 into 10 raised to the power 23. Alright. So after performing the calculations, we find that the molecular volume V is approximately 8.51 cubic centimeter. This result gives us the volume occupied by 1 mole of oxygen molecules, considering their size. Next, we calculate the fraction of molecular volume to the actual volume of oxygen gas. This is done by dividing the molecular volume by the actual volume at STP, which is 22,400 cubic centimeters. Alright, so fraction of molecular volume to the actual volume of oxygen is 3.8 into 10 raised to the power minus 4. This small fraction indicates that the molecules occupy a very teeny portion of the total volume, highlighting the vast amounts of empty space in gases. Molar volume is the volume occupied by 1 mole of any ideal gas at standard temperature and pressure. Standard temperature and pressure means pressure is 1 atmospheric pressure and temperature is 0 degrees Celsius, so that it is 22.4 liters. Alright, let's see the solution. To solve this problem, we need to consider the given conditions. First, we have the standard temperature, which is 0 degrees Celsius. In Kelvin, this is 273.15 Kelvin. Remember, converting to Kelvin is essential because the gas laws require absolute temperature. Next, we have standard pressure, which is 1 atmospheric pressure. So 1 atm is equal to 101325 Pascal, or we can say 1.01 into 10 raised to the power 5 Pascal. Number of moles, N equal to 1 mole. Universal gas constant R is equal to 8.314 joule per mole per Kelvin. Alright. So, ideal gas equation relating pressure P, volume V and temperature T is given as PV equal to nRT. This equation helps us relate these variables to each other, where universal gas constant R is equal to 8.314 joule per mole per Kelvin. N equal to number of moles, which is equal to 1. Standard temperature 273 Kelvin. And pressure 1 atm, which is equal to 1.013 into 10 raised to the power 5 Newton per meter square. Now, volume of gas is related to amount of substance, temperature and pressure. So we use the ideal gas law, which is expressed by as V equal to nRT divided by P. Here V is the volume, N is the number of moles and T is the temperature, R is the universal gas constant, P is the pressure. This equation will help us calculate the molar volume. So now let's substitute the value into the equation. We have 1 mole of gas, R is 8.314 joule per mole Kelvin, T is the 273 Kelvin and P is 1.013 into 10 raised to the power 5 Pascal. This substitution allows us to calculate the volume in cubic meters. After performing the calculation, we find that V equals 0.0224 cubic meters. Remember, 1 cubic meter is equivalent to 100 liters, 1000 liters. Alright, 1 cubic meter is equal to 1000 meters. Converting the volume to liters, we find that V equals to 22.4 liters. This confirms our initial statement about the molar volume of an ideal gas at STP. It's important to note this standard value for future reference. So we can say the molar volume of a gas at standard temperature and pressure is 22.4 liters. An oxygen cylinder of volume 30 liters has an initial gauge pressure of 15 atm and a temperature of 27 degrees Celsius. After some oxygen is withdrawn from the cylinder, the gauge pressure drops to 11 atm and its temperature drops to 17 degrees Celsius. Estimate the mass of oxygen taken out of the cylinder. R equal to 8.31 joule per mole per Kelvin, and molecular mass of oxygen gas is equal to 32 U. Here you have to find out the mass of oxygen taken out the cylinder. Let's see the solution. We will start by listing the given information. First, we have the volume of the cylinder, which is 30 liters. Alright. Initial gauge pressure P1 equal to 15 atm. Initial temperature T1 equal to 27 degrees Celsius. So here we need to convert degrees Celsius to Kelvin by adding 273. So it will be 300 Kelvin. Final gauge pressure P2 equal to 11 atm. Final temperature T2 equal to 70 degrees Celsius. Again here we have need to convert this degrees Celsius to Kelvin by adding 273. So it will be equal to 290 Kelvin. Gas constant R equal to 8.31 joule per mole per Kelvin. Molecular mass of oxygen is equal to 32 U. Universal gas constant R equal to 8.314 joule per mole per Kelvin. Alright. Now, first we need to determine the initial number of moles of oxygen gas in the cylinder. To find the number of moles, we will use the ideal gas equation. The ideal gas equation is expressed as P1V1 is equal to N1RT1. Here P1 is the initial pressure, V1 is the volume, N1 is the number of moles, R is the universal gas constant, and T1 is the initial temperature. This equation will help us solve for number of moles. So rearranging the ideal gas equation, we find that N1 is equal to P1V1 divided by RT1. This formula allows us to calculate the initial number of moles by plugging into the known values for pressure, volume and temperature. So substitute the given values into the equation. We have N1 is equal to 15.195 into 10 raised to the power 5 into 30 into 10 raised to the power minus 3 divided by 8.314 into 300. So solving this, we find that N1 is equal to 18.276. Alright, 18.276 moles. Now we know N1 is equal to M1 divided by M. Initial number of moles of oxygen is small n1. In terms of its mass, we use the formula N1 is equal to small m divided by capital M, where small m1 is the initial mass of oxygen and capital M is the molecular mass. So understanding these, the molecular mass of oxygen is 32 grams per mole. Alright, now to calculate M1, we have the formula N1 into capital M. So just put the values. So it will be 18.276 into 32. So solving this, you will be get 584.84 grams. Alright. Now, after some oxygen is withdrawn from the cylinder, the pressure and temperature reduces. So, let N2 be the number of moles of oxygen left in the cylinder. N2, which represents the number of moles of oxygen left in the cylinder after some with time. So, ideal gas equation is given as P2V2 is equal to N2RT2. We can rearrange the ideal gas equation to solve for N2. So N2 equal to P2V2 divided by RT2. This formula allows us to calculate the number of moles of oxygen left in the cylinder using the known values of pressure, volume and temperature. So let's substitute the given values into our equation. So N2 is equal to 11.143 into 10 raised to the power 5 into 30 into 10 raised to the power minus 3 divided by 8.314 into 290. So after performing the calculation, we find that N2 is equal to 13.86 moles. Alright. To find the oxygen remaining, we start by expressing the number of moles N2 in terms of mass and molar mass. Here N2 equals to the mass of remaining oxygen divided by its molar mass M. Now let's clarify that M2 represents its mass of oxygen that remains in the cylinder after some has been withdrawn. So we can express M2 as N2 times M. So substituting the values, we find that M2 equals 13.86 into 32 gram per mole, which gives us 453.1 grams. Alright, so mass of the oxygen taken out of the cylinder is initial mass of the oxygen in the cylinder minus final mass of the oxygen in the cylinder. So mass of oxygen taken out of the cylinder is equal to M1 minus M2, and mass of oxygen taken out of the cylinder is equal to 584.84 gram minus 453.1 gram. So mass of the oxygen taken out of the cylinder is equal to 131.74 gram by subtracting the final mass from the initial mass. So the mass of oxygen taken out in kilograms, we need to convert 131.74 grams to 0.13 kilograms. This conversion is important for consistency in units, specifically when dealing with scientific calculations where SI units are preferred. Therefore, 0.131 kg of oxygen is taken out of the cylinder. An air bubble of volume 1.0 centimeter cube rises from the bottom of a lake 40 meter deep at a temperature of 12 degrees Celsius. To what volume does it grow when it reaches the surface, which is at a temperature of 35 degrees Celsius? Let's see the solution. Let's start by identifying what we know. We have an air bubble with initial volume of 1.0 centimeter cube. This is the volume at the bottom of the lake, and we will need to convert it cubic meters for our calculations. So it will be 1.0 into 10 raised to the power minus 6 meter cube. Bubble rises to height d equal to 40 meter. Temperature at a depth of 40 meter, T1 is equal to 12 degrees Celsius, and we need to convert it in Kelvin by adding 273. So it will be 285 Kelvin. Temperature at the surface of the lake, T2 is equal to 35 degrees Celsius, which converts to 380 Kelvin. This increase in temperature will cause the bubble to expand as it rises. Now let's consider the pressure at the surface of the lake. It's given as 1 atm, which we convert to pascals for our calculations. This is the standard atmospheric pressure. So P2 is equal to 1 atm, or we can say 1.013 into 10 raised to the power 5 Pascal. Alright. So the pressure at the depth of 40 meter, P1 is equal to 1 atm plus d rho g. Here P1 represents the total pressure at the depth. Now the terms here, rho is the density of water, that is 10 raised to the power 3 kilogram per meter cube. G is the acceleration due to gravity, is equal to 9.8 meter per second square. So just substitute these values into our equation. We find that P1 is equal to 1.013 into 10 raised to the power 5 plus 40 into 10 raised to the power 3 into 9.8. So solving this, you will be get 493300 Pascal. This gives us the pressure at the depth of 40 meters. Alright. So ideal gas law in a form that relates initial and final states, P1 V1 upon T1 is equal to P2 V2 upon T2. This equation helps us understand how pressure, volume and temperature are interrelated for a gas. So in this equation, V2 represents the volume of the air bubble when it reaches the surface. Now we rearrange the equation to solve V2. So V2 is equal to P1 V1 T2 divided by T1 into P2. So let's substitute the known values into the equation. So V2 is equal to 493300 into 1.0 into 10 raised to the power minus 6 into 308 and divided by 285 into 1.013 into 10 raised to the power 5. So V2 is equal to 5.263 into 10 raised to the power minus 6 meter cube. This gives us the volume in cubic meters, which is a standard units in physics. So converting the volume to cubic centimeters, we have V2 is equal to 5.263 centimeter cube. So when the air bubble reaches the surface, its volume increases to 5.263 centimeter cube. Estimate the total number of air molecules inclusive of oxygen, nitrogen, water vapor and other constituents in a room of a capacity 25.0 meter cube at a temperature of 27 degrees Celsius and 1 atm pressure. Here you have to find out the total number of air molecular in a room capacity 25.0 meter cube. Alright, let's see the solution. Given terms, we have the volume of the room which is given as 25.0 cubic meters. Remember, volume is a measure of how much space something takes up. Temperature of room, it is given as 27 degrees Celsius, which is need to convert to Kelvin for our calculations. In Kelvin, this temperature is 300 Kelvin. Always remember to convert temperature to Kelvin when using the ideal gas law. So pressure in the room is given as 1 atmosphere. We convert this to pascals, which is the SI units for pressure. So 1 atm is equivalent to 1.013 into 10 raised to the power 5 pascals. Now we have all given values. We can use the ideal gas equation. This equation relates pressure, volume and temperature to the number of molecules. So PV is equal to KB and T. So KB is the Boltzmann constant. Is numerical value is 1.38 into 10 raised to the power minus 23. And is the number of air molecules in the room. Alright. The total number of air molecules in the room is N is equal to PV divided by KBT. To find the number of molecules, here P is the pressure, V is the volume, KB is the Boltzmann constant and T is the temperature in Kelvin. So now let's substitute the values into the formula. So N equal to 1.013 into 10 raised to the power 5 into 25 divided by 1.38 into 10 raised to the power minus 23 into 300. Here we convert the temperature to Kelvin by adding 273 to the Celsius temperature. So after performing the calculation, we find that N is equal to 6.11 into 10 raised to the power 26 molecules. Therefore, the total number of air molecules in the room is 6.11 into 10 raised to the power 26. Estimate the average thermal energy of a helium atom at first room temperature 27 degrees Celsius, second the temperature on the surface of the sun 6000 Kelvin, third the temperature of 10 million Kelvin, the typical core temperature in the case of a star. Let's see the solution. So let's begin by listing what we know. We have the temperature at which we want to calculate the average thermal energy. First we will consider room temperature, which is 27 degrees Celsius. This equivalent to 300 Kelvin. Alright. Now we will use the formula for average thermal energy, which is given by the 3/2 times of the Boltzmann constant times the temperature, or 3/2 kT. So average thermal energy is equal to 3/2 kT. Here K is the Boltzmann constant, which is a fundamental constant in physics. Its value is 1.38 into 10 raised to the power minus 23 meter square kg per second square per Kelvin. This constant relates the average kinetic energy of particles in a gas with the temperature of the gas. Alright. So after performing the calculation, we find that average thermal energy is, after calculation, 6.21 into 10 raised to the power minus 21 joule. Alright. Hence the average thermal energy of a helium atom at room temperature is 6.21 into 10 raised to the power minus 21 joule. On the surface of the sun, T equal to 6000 Kelvin. So average thermal energy is equal to 3/2 kT. Here is the energy, K is the Boltzmann constant and T is the temperature in Kelvin. So now let's substitute the values into the formula. E is equal to 3/2 into 1.38 into 10 raised to the power minus 23 into 6000. Notice how we use the Boltzmann constant. So 1.38 into 10 raised to the power minus 23 joule per Kelvin, which is important for these calculations. So after performing the calculation, we find that E is equal to 1.241 into 10 raised to the power minus 19 joule. Hence the average thermal energy of a helium atom on the surface of the sun is 1.241 into 10 raised to the power minus 19 joule. Alright. Now, at temperature T is equal to 10 raised to the power 7 Kelvin, the average thermal energy E equal to 3 by 2 T. Here E represents the average thermal energy, K is the Boltzmann constant, and T is the temperature in Kelvin. So let's substitute the value into the formula. So E equal to 3 by 2 into 1.38 into 10 raised to the power minus 23 into 10 raised to the power 7. So solving this, you will be get E is equal to 2.07 into 10 raised to the power minus 16 joule. Hence the average thermal energy of a helium atom at the core of a star is 2.07 into 10 raised to the power minus 16 joule. Three vessels of equal capacity have gases at the same temperature and pressure. The first vessel contains neon, monatomic, second contains chlorine, diatomic, and third contains uranium, hexafluoride, polyatomic. Do the vessels contain equal number of respective molecules? Is the root mean square speed of molecules the same in the three cases? If not, in which case is Vrms is largest? Let's see the solution. So let's start by addressing the first part of the question. Yes, all three vessels contain the same number of molecules. This is because they are at the same temperature and pressure, and according to Avogadro's law, equal volumes of gases at the same temperature and pressure contains an equal number of molecules. Second, now let's consider the root mean square speed of the molecules. The answer is no. The root mean square speed is not the same for all gases. Among the three, neon has the largest root mean square speed. This is because the speed is inversely related to the mass of the gas molecules. To understand why the number of molecules is the same, remember that the vessel have the same capacity, meaning they have same volume. Since each gas is at same pressure, volume and temperature, we can confidently apply Avogadro's law. This law is a fundamental in understanding the behavior of gases under these conditions. So according to Avogadro's law, three vessels will contain an equal number of respective molecules. This is equal to Avogadro's number and is equal to 0.6.023 into 10 raised to the power 23. And the root mean square speed of a gas of mass m and temperature T is given by the relation. So Vrms is equal to under root 3 kT divided by m, where K is the Boltzmann constant. Alright. For the given gases, K and T are constants. Hence Vrms depends only on the mass of the atoms. That is, Vrms is inversely proportional to under root m. Therefore, the root mean square speed of molecules in the three cases is not the same. Among neon, chlorine and uranium hexafluoride, the mass of the neon is the smallest. So hence neon has the largest root mean square speed among the given gases. Alright. At what temperature is the root mean square speed of an atom is an argon gas cylinder equal to the RMS speed of a helium gas at atom at minus 27 degrees Celsius. Atomic mass of argon is 39.9 U of helium, or helium is equal to 4.0 U. So let's start by identifying the given information. We know the temperature of the helium gas atom is minus 27 degrees Celsius, which converts to 253 Kelvin. Alright. Next we have atomic mass of argon, which is 39.9 atomic mass units, 39.9 U. Atomic mass of helium, 4 U. Alright. So let's VRMS argon with the RMS speed of argon, and VRMS helium with the RMS speed of helium. The RMS speed of an argon is given by VRMS argon is equal to under root 3 RT argon divided by M. So solving this, you will be get the VRMS AR, where R is the universal gas constant, TAR is the temperature of argon gas. Alright. Now to solve this, we start by considering the RMS speed of helium. The formula for RMS speed is VRMS is equal to root 3 RT by M. Alright. So it is given that VRMS is equal to VRMS helium. So now let's look at the formula of root mean square speed in detail. So it will under root 3 RT argon upon M is equal to under root 3 RT helium upon M. So square root cancel out. Similarly, R cancel out, M and 3 cancel out, and remaining term TAR upon MAR is equal to T helium upon M helium. So finally, we solve the temperature of argon by rearranging the equation. We express the temperature of argon in terms of known temperature of helium and their respective molar masses. This gives us the clear formula to calculate the desired temperature, illustrating the impact of atomic mass on the speed of gas particles. Now, solving for the temperature of argon denoted as TAR. So just substitute the values into the equation. We have TAR is equal to 253 by 4 into 39.9. Here 253 is the temperature in Kelvin for helium at minus 20 degrees Celsius, and 39.9 is the atomic mass of argon. So TAR is equal to 2523.675. So TAR is equal to 2.52 into 10 raised to the power 3 Kelvin. This is a concise way to express the temperature, making it easier to communicate. Therefore, the temperature of argon is 2.52 into 10 raised to the power 3 Kelvin. Estimate the mean free path and collision frequency of a nitrogen molecule in a cylinder containing nitrogen at 2 atm and temperature 70 degrees Celsius. Take the radius of a nitrogen molecule to be roughly 1.0 angstrom. Compare the collision with the time the molecules move freely between two successive collisions. Molecular mass of N2 is equal to 28.0 U. Let's see the solution. So we have some given values that will help us in our calculations. First, we have the mean free path, which is average distance a molecule travels before colliding with another molecule. It is given as 1.11 into 10 raised to the power minus 7 meter. Alright. Pressure inside the cylinder containing nitrogen, P is equal to 2 atm. So in Pascal, it will be 2.026 into 10 raised to the power 5 Pascal. Temperature inside the cylinder, T equal to 17 degrees Celsius. In Kelvin, it will be 290 Kelvin. Radius of nitrogen molecule, R is equal to 1 angstrom. And diameter, it will be 2 into 1 into 10 raised to the power minus 10. It will be 2 angstrom. Molecular mass of nitrogen, 28 gram. In kg, it will be 28 into 10 raised to the power minus 3 kg. So root mean square speed of nitrogen is given by the relation VRMS is equal to under root 3 RT by M. R is the universal gas constant, T is the temperature in Kelvin, and M is the molar mass of the gas. So substituting the values in the equation of Vrms, so it will be under root 3 into 8.314 into 290 divided by 28 into 10 raised to the power minus 3. So Vrms is equal to 508.26 meter per second. Alright. Now mean free path is given by the relation. The mean free path denoted as L, it's given by the equation L is equal to kT by under root 2 d square into P. Here K is the Boltzmann constant, T is the temperature and temperature in Kelvin, and D is the diameter of the molecule, and P is the pressure. So the relation is this one, kT upon root 2 d square into P. So substituting the values in the above equation, so it will be 1.38 into 10 raised to the power minus 23 into 290 divided by root 2 into 3.14 into 2 into 10 raised to the power minus 10 whole square into 2.026 into 10 raised to the power 5. So solving this, you will be get 1.11 into 10 raised to the power minus 7 meter. So collision frequency, which is ratio of the root mean square speed velocity to the mean free path L. So now we will substitute the known values in our formula. So it will be 508.26 divided by 1.11 into 10 raised to the power minus 7. This gives a numerical value for the collision frequency. So it will be 4.58 into 10 raised to the power 9 per second. This high frequency indicates that nitrogen molecules collide very often in the given conditions. It's important to note how this frequency relates to the behavior of the gases. Now collision time is given as D upon Vrms. So just put the value 2 into 10 raised to the power minus 10 divided by 508.26. So solving this, you will be get 3.93 into 10 raised to the power minus 13 second. So time taken between successive collisions. This is an important concept because it tells us how long a molecule moves freely before hitting another molecule. So T prime equal to L by Vrms. So just put the values and you will be get the T prime equal to 2.18 into 10 raised to the power minus 6 10 second, and so take the ratio. So we will get 2.18 into 10 raised to the power minus 10 divided by 3.93 into 10 raised to the power minus 13. This ratio will gives us a sense of how much longer the molecule move freely compared to the time it spends in collision. So T prime upon T is equal to 500. Hence the time taken between successive collisions is 500 times that taken for a collision. Thank you for your attention.